Welcome to the H2O channel. This is Physics by the H2O. Today we are going to be doing physics, and the topic we are going to consider today will be refraction of light wave. Now, what does refraction means? Refraction means the change in the speed, direction, and wavelength of a wave when it moves from one medium to another of different densities. Now, we have different properties of wave. We have reflection, we have diffraction, we have polarization. But today we are going to be considering refraction of light wave. And refraction, like I said earlier, is the change in the speed. I want you to take note of this important term, the change in direction and the change in the wavelength of a wave when it moves from one medium to another of different densities. So this simply means that if your wave moves from one medium to another, as long as the medium do not have the same densities, refraction is bound to occur. Don't forget, there's a material called opaque material. What are opaque material? Opaque material are those materials that do not allow light to pass through them. So what you can probably observe from opaque material is reflection of light. Okay? There are materials called transparent materials. What are transparent materials? Transparent materials are those materials that can allow light to pass through. A large amount of light can pass through a transparent material. And then we have what we call translucent. Though the light will pass through, but there's only small amount of light that will pass through it. Now, if you go back to this transparent material, like I said earlier, you discover that large amounts of light will pass through every transparent material. And it is in transparent material that we'll probably observe the effect of refraction of light. Like I said before, refraction means the change in speed, change in direction, and change in the wavelength of a wave. Why? Because as the light moves from one medium to another of different densities, the direction, wavelength, and the speed is bound to change. And I want you to know something, that there are three major parameters of wave, three major variables of wave. And what are the variables? We have speed, which is V, we have frequency, which is F, and we have wavelength, which is denoted as a symbol called lambda. So you discover that in refraction of light wave, the speed will change, the wavelength will change. The only parameter or variable that will not change in refraction of light wave is your frequency. So I want you to know that refraction occurs at a constant frequency. So the frequency remains constant while your speed and your wavelength changes. Now, I want you to also know that if light moves from air to water, refraction is bound to occur because the density of air and the density of water is not the same. If light moves from water to glass, refraction will also occur. Why? The density of water and the density of glass, they are not the same. So refraction only occurs when waves move from one medium to another medium of different density. So we can see that light can move from air to water, or from water to air, or water to glass, or glass to water. So as long as it moves from one medium to another, one transparent medium to another of different densities, refraction is bound to occur. So we are going to be looking at the refraction of light on a triangular glass prism, and that's what we want to consider right now. We are going to look at the refraction of light on a rectangular glass prism. We have refraction of light in a triangular glass prism. We have refraction in a rectangular glass prism. So, but for today's class, we are going to be looking at the refraction of light wave in a rectangular glass prism. Okay? Now, this is your rectangular glass prism that you have in your school laboratory. We are going to be looking at the refraction of light wave in a rectangular glass prism such as the one that you are seeing right now. Okay? Now don't forget, in the construction of your ray diagram, you must first of all draw your normal. Your normal is a line that is drawn perpendicular to any surface. So I'm going to draw our normal here, okay? And this normal, the point where the normal meets with the mirror, with the glass, I will label it as O. So let's call this normal N1, okay? Now, the reason why I call this normal N1, because this is the first interface. At the other interface, I'm going to label the normal as N2. So please take note, the normal is an imaginary line that is drawn perpendicularly to a plane surface. So you see that a ray of light coming like this is our incident ray. Now, if an incident ray strikes a glass prism, don't forget this is air and this is glass. The density of air and the density of glass is not the same. So when light moves from air to glass, this is what is going to happen. Refraction is bound to occur. And don't forget that refraction is a change in speed, change in direction, and change in wavelength. So this is what we are going to observe. The ray is not going to continue this way. No. This is not how the ray is going to be. Instead, the ray will bend. And when it bends, it goes like this. This is what we call the refracted ray. Please do not confuse this with reflection. Reflection means the bouncing back of a wave. So this one is your incident ray. This is your refracted ray. And then you discover that this second interface can also have its own normal. So I'm going to label it as N2. So this is normal at the first interface, while this is normal at the second interface. Okay? Now, as soon as the ray of light, which is the refracted ray, is leaving the prism, it's going to bend again. Okay? Then don't forget I said this is the incident ray, this is the refracted ray. This ray is called the emergent ray. What does an emergent ray mean? It simply means refracted ray that emerge out from the glass prism. Okay? This is your incident ray, this is your refracted ray, while this is your emergent ray. Now, what is happening in this place is that the speed is changing. The wavelength is changing. The speed of light in air is 3 times 10 raised to the power of 8 meters per second. That's the speed of light in air. But when the speed gets to this glass, the speed is bound to reduce. Okay? And if the speed reduces, we'll say that the speed of light in glass is approximately 2.0 times 10 raised to the power of 8 meters per second. Now, though this value might vary depending on the refractive index of the glass, okay? But for most glasses, where the refractive index is around 1.5, our speed is approximately 2.0 times 10 raised to the power of 8 meters per second. This is speed of light in air, this is speed of light in glass. So if light moves from air to glass, the speed will reduce, as you can see on the board. And then you see now that the ray of light has bent. Okay? Now, this air is a less dense medium, in the sense that the density here is lower than this. This one is more dense medium. So what do we observe in this place is that if light wave moves from a less dense medium to a more dense medium, the ray of light, which is the refracted ray, will bend towards the normal, as you can see in this diagram, okay? But when it moves from a dense medium now to a less dense medium again, you will still observe that it will bend away from the normal, okay? So at the first place, it's bending towards the normal. At the second place, it's bending away from the normal. Now, what we have to do here again is to know our angle of incidence, our angle of refraction, and our angle of emergence, okay? Now, this is our normal. The angle between your incident ray and your normal is called the angle of incidence. So I'm labeling this place as I. This is called angle of incidence. The angle between your refracted ray and this normal is called the angle of refraction. So permit me to write arrow 1 here. This arrow 1 indicates that it is the angle of refraction in the first phase. Because if you come over to this place, you are still going to see another angle here, which is also the angle of refraction in the second phase. So you have arrow 2 here. So we can label this as arrow 1 and label this as arrow 2. This is the angle of refraction in the first phase. What is this angle of refraction in the second phase? And then this is your emergent ray, and this is also your normal. The angle between your emergent ray and your normal is called the angle of emergent. Finally, before we come to the end of this video, I would like for you to know that your angle of incident at this point is equal to your angle of emergence. Okay, your angle of incident here is equal to your angle of emergent. That is to say, this is air. Don't forget, this is air and this is also air. So the angle here and the angle here are what? The same. Now, if you look again, you'll find out that this is the incident ray and this is the emergent ray. And if you look very well, you will see that the incident ray is parallel to the emergent ray. So what does that mean? It means that there is no deviation. There is no angle of deviation between the incident ray and the what? Emergent ray. The only thing we have here is just that the ray of light was displaced through an angle which is in this place. So we can call this the angle of displacement. Okay? So in our next video, we are going to be looking at calculations involving refraction, where we are going to consider the first and the second laws of refraction. If today is your first time for coming across this video, please don't forget to subscribe so that whenever we post our video, you always get our notification. And then when you do that, you can like and share. Thank you very much. Until I see you in our next video.